Good morning and welcome back to today's NASA Future Forum live from the University of Maryland College Park in the Riggs Alumni Center. I'm Dave Steeds from NASA's Office of Communications. We're now going to continue on with this morning's panelists. We have our next panel titled Technology and Innovation, Unleashing the Power of Technology and Creativity. And the panel is going to be led by our own Peter Hughes, who is the Chief Technologist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Peter?
Thank you. So I'm quite honored to be here today to host this panel session on innovation and technology and how we go about unleashing the creative power of such. Before I do such, I want to have a few introductory remarks about innovation and technology and some of the important milestones. Of course, we heard earlier from Charlie that we had a real critical milestone at the end of the chapter of this shuttle. And granted, it is a very bittersweet milestone, but it's kind of eclipsed some other real important milestones recently. One of which is that the agency now has a chief technologist, Dr. Bobby Braun, who we heard from this morning. Each of the centers have a center chief technologist that work with Bobby and operate under the Center Technology Council to provide him guidance and to work issues across centers, providing guidance of the future directions of technologies. But we also have an important milestone in the sense that we have a new organization at headquarters, the Office of Chief Technologist, with budget. We have some initial budget this year under the FY11 operating plan. And we have just released some very important awards to some students, about 80 students for the NASA Space Technology Research Fellowship. This is a huge milestone where we're going to engage students from across the nation in some very cutting-edge technology. Earlier this week, we just announced some new awards, 40 awards or 30 awards for NIAC. Some very creative, almost implausible technologies that are going to create the new future and engage and inspire people of the power of what we can do. These are all very significant, and it's further testament of the importance of us of continuing to focus on innovation and technology. I think no one in this room will disagree that innovation and technology is important. We all kind of have our own perspective of how to go about innovation and technology. What I've assembled here today is a panel with people from across the enterprise, the NASA enterprise, from within the agency, from industry and academia. They're going to give different perspectives on how we stimulate creativity and innovation, and different perspectives of how we could bring in the broader set of innovators from throughout the nation and beyond. We're going to start the panel this morning with Mr. Joe Parrish, who's the Director of Early Stage Innovation in the Office of the Chief Technologist. He has a very broad background, working spaceflight programs, worked at JPL. He also worked in industry. He was a performer in the SBIR program. Just a great example of someone who's jumped around throughout the industry to help contribute to our NASA program. When I spoke to him, and as I did with every panelist, I tried to get a little tidbit that was unique about that individual. And I found out that he has a twin brother. I also found out he's an avid pilot and glider for gliders. But he also flies a small hand-built plane, a small custom plane. And he's so trusting of his brother. His twin brother was one who made this plane. I find that quite remarkable, to trust his brother so much, to put his hands into his brother's ability to build something. So with Joe. Joe's going to talk a bit about how we plan to engage a wide spectrum of innovators throughout the space enterprise for innovation and technology.
Great. Thank you very much, Peter. And the only remark I would add to the little personal note about my twin brother, the only thing I can really say about him, in addition to being an excellent aircraft builder, he's an incredibly handsome guy. And so those two qualities really define him. To really get to the much more interesting and important point, I wanted to talk a little bit about how we can foster innovation and how we tap into the broadest possible spectrum of participants in innovation. And one of the most important fundamental things to realize about innovation is some of the things that we do in NASA are very resource and capital intensive. It takes hundreds or thousands of people to launch a rocket into space. And those activities, just by their very nature, can sort of only be performed by a handful of organizations. But when we back up and we think about innovation, and we think about the fundamental notion of taking ideas and applying them to challenging problems, innovation doesn't require any capital. Innovation doesn't require giant teams. It comes from our individual brains. And all of us are equipped with that. We just have to spend those mental clock cycles in application to these challenging problems. And so one thing I think that NASA has done really nicely, especially in recent emphasis in developing our programs in space technology, and Peter mentioned them, the administrator mentioned some of them earlier, and our panelists earlier today have mentioned them. We're approaching the innovation process from a variety of perspectives, and just within the Office of the Chief Technologist, we have a variety of programs that try to engage different segments of the aerospace community, but even the broader population in the innovation process. And the one that I think is one of the most wonderful examples is our Centennial Challenges program. That is a prize-oriented program where NASA establishes prizes for the achievement of challenging objectives. And the prize competitions are open to anyone in the country to come and participate. And in fact, some of the most incredible achievements on the way to winning these prizes have been achieved by individuals operating in their homes, on their dining room tables, and their garages, to come up with new approaches to solving some of the problems that have vexed NASA for the last 20 years. And we call this program the one that is trying to engage the citizen inventor. And I think that it's really a remarkable opportunity. We're about to have a competition in California in September to and this is near and dear to my heart, to dramatically increase the efficiency of general aviation aircraft, looking for 5 to 10x improvement over the current state of the art in general aviation aircraft efficiency. And that prize is $1.5 million offered by NASA to someone who can develop an aircraft that can achieve 200 passenger miles per gallon, where a Cessna gets about 20 right now. We have some other programs and different approaches that are a little narrower in scope, but when I sort of rattle these off quickly, you'll get the impression that we're coming at it from so many different directions that we really managed to capture the full spectrum. The NIAC program, Peter just mentioned, we issued 30 awards. The barrier to entry into that program was remarkably low. It was a 9-page proposal that could be written by anybody, and we got hundreds of proposals from academia, from industry, from small businesses, from NASA, and we have 30 projects, any one of which, if they were successful, would really be revolutionary and would completely change the way that we approach space exploration or mitigation of orbital debris. A number of different challenges are being addressed in this program, and that was open to anyone who wanted to participate, anyone in the nation who wanted to participate. We have the SBIR program, which is a little bit narrower in terms of the entities that can engage. It's oriented towards small businesses, and the reason for that is the small businesses are really one of the major engines in innovation in the country. These businesses that are 10 people or 50 people or 100 people, even when they're starting to build and grow in their size, are so agile and able to respond quickly and able to look into other areas for ideas that can be transferred and applied to new problems that NASA has. We have the Center Innovation Fund, which Peter actually administers on behalf of the Goddard Space Flight Center. We also are providing funding to all of the other NASA centers to tap into the creative energies of the people at the NASA centers who really are in the trenches on a daily basis trying to address NASA problems. So I've only mentioned a few, and I wanted to close with just one that's been mentioned a few times today. Because we're in an academic setting, I really have to talk a little bit about the Space Technology Research Fellowships Program. And Claudia Meyer, who's the program executive for that program and has really been the shepherd of that idea. She's in the audience today and greatly appreciative of everything that she's done to make that happen. But last month we selected 80 brilliant young innovators who are going to be the future of NASA's innovation. And we have this really cool little slogan, and it's go to school, invent technology, define the future, save the world. And you start out at the beginning of that and you say, go to school. That sounds kind of easy, right? Go to school. And then invent technology. Well, yeah, we're all about that. And then you get to the part where you're talking about save the world. And it seems hard. But when you start at the beginning and you take one step, it's not impossible to think about one of these brilliant young people pursuing a solution to mitigating an asteroid that could threaten our planet, or making possible the colonization of other planets, so if for one reason or another this planet becomes too crowded or too difficult to populate, we can migrate to another one. Now, these are ideas that are not going to be realized for decades, but we have to get started today on doing that. And this Space Technology Research Fellowships Program with the inaugural class of 80 is a magnificent way of getting started on that path. And the other cool thing is that Dr. Ray Sedgwick, who actually had a very insightful question earlier today, is a professor here at the University of Maryland, and one of his graduate students won one of these fellowships. So he and Claudia have been talking about how to make best use of this brilliant new researcher. So let me conclude by saying that I've only given you a small snapshot of a number of the different ways that we're approaching the development of technology, the ways that we're trying to foster innovation from the broadest possible spectrum of not just our aerospace community, because as Ray said earlier, it's a rather small slice of it, but broadening out to all of the nation and getting people to think about how to solve NASA's big problems. So thank you.
Great, thanks, Joe. So for our next speaker, we have Ms. Jennifer Byrne from Lockheed Martin. She's a VP of Corporate Engineering and Technology. Jen's a science and engineer by training. She has program management and technical leadership experience for complex, very large-scale systems. I mean, talking with her, trying to understand what her avocations were, I was asking what she does in her spare time. And she kind of laughed at it and said she doesn't have spare time. It's because she's pursuing a PhD at GW University in systems engineering, and a really interesting topic of optical cochlear implants and how we can explore new ways to fire the nerves using optical signals as opposed to other electrical signals, using very advanced techniques for modeling and simulation to understand this phenomenon and how it might work. But a great example of how we could take a cross-cutting set of technologies and apply it to our daily life. So Jen's agreed to talk about how collaboration can positively impact innovation. Jen?
Thank you, Peter. And probably all of my professors are watching me on television and saying, shouldn't she be studying? Yeah. Probably. And so I think it's a really important topic to think about collaboration enabling innovation, because innovation requires thinking differently. If you think about some of the major innovations that we've experienced over the past 50 years or so, a few come to mind. One is Einstein and the theory of relativity, and it really came because he had to think about time differently. There was an inability on his part to really process the concept of time, and so he really went about that mathematically and invented a new discipline. Same thing with Fourier optics. We used to look at wave tracing, and that's kind of my background, is coherent imaging. But Fourier optics really changed that field because it was a blend of mathematics and optics. So that's the thing. Thinking differently is really important. And so if you think about collaboration, what collaboration gives us automatically is diversity. And nature loves diversity. Diversity of thought, background, education, and specifically is one of the many reasons that we need to increase the underrepresented populations in science, technology, engineering, and mathematics, because that diversity of perspective gets us better solutions. and gets that different thinking. The collaboration is really important because when you collaborate across boundaries, you're automatically getting that diversity of perspective. And as a group, the group becomes more intelligent. And so I call that collective intelligence. And it's kind of ironic because we're just talking about me going for my PhD, and we spend a lot of time in trying to increase individual intelligence through education and through various other types of training. As a leader in a technology world, I feel one of our greatest untapped resources is collective intelligence. And it doesn't come automatically. It's not just bringing diverse groups together because, if I think one way and you think a different way, there's a discomfort that comes from that when somebody is challenging kind of your mindset. So as leaders, it's really important that we develop these new ways of bringing together diverse teams to collaborate, and everyone feels valued because the overall solution is a better solution. So that was the point I'd like to make, and thank you.
Great, thank you. It's actually a great segue to our next speaker, who's Dr. Pat OShea. He's the VP for Research and a senior research official here at University of Maryland, College Park. Has a varied background in academia, also worked at Los Alamos National Labs, where he explained one of the most interesting and one of the funnest jobs he had, where he was the launch pad chief down out at White Sands for some early experiments in space physics for the DoD. Pat has agreed to talk about how the universities play a role in R&T and in developing our next generation of innovators.
Thank you, Peter. I've been Vice President for Research here at the University of Maryland for 6 weeks. In fact, it'll be 6 weeks tomorrow. And so people ask me, what does a Vice President for Research do? And I found in answering that question, it's not so much what I do as a Vice President, but what is a research university and what is the role of a research university in society. There are about 2,600 four-year colleges and universities in the United States, but a very small fraction of those are research universities. If you look at the American Association of Universities, which is the organization that represents the major extensive research universities in the United States, it only has 61 members. That's a very, very small fraction of the total number of colleges and universities in the United States. So research universities are in the business of doing three things in closing a triangle. One is doing research, which is the creation of knowledge and technology. The other is education, which is the passing of that new knowledge and technology on to students. And the third is service, which is connecting that research and education and producing output through both the educated students and the technology that we develop, and transferring that to industry and to government. And there are, as I said, very few universities in the country which really take the three aspects of that seriously. And when it comes to the type of technologies we're talking about today for NASA, these technologies are very rapidly evolving. So that when students come in to the university in the fall and when they leave 4 years from now, there will be jobs available for them that did not exist when they came in. And remember, Facebook, one of the biggest companies in the United States, that was only founded a few years ago. It didn't exist in 2004, 2005. So we are training and educating students for jobs that do not exist, for technologies that are not yet named. So at research universities, we are in the business of educating explorers and not simply training tourists. Because explorers synthesize knowledge, explorers observe, question, associate, network, and experiment, to quote a new book called Innovators DNA. They go beyond the map, whereas tourists work very much within the map. So at the major research universities, we try to break down the silos. We don't just talk about multidisciplinary or interdisciplinary research and education. We talk about transdisciplinary, which goes beyond the tradition. Nobody ever received an education in the classroom. If I actually think of how much I remember from my undergraduate education, I could probably fit it on one page. It's what I learned outside the classroom. We used to call it extracurricular activity, but at the research universities, we're making the extracurricular activities part of the curriculum. That is competition-based learning, multidisciplinary teams. We have at the University of Maryland, the very first class for engineers is an introduction to engineering design, where students have to design and build a hovercraft, and their final grade is based on a public competition that they have to engage in front of the public. And that is very stimulating because it brings together a large number of students in teams that would not ordinarily get together, but it trains them and educates them in a very much a real-world environment. The other thing we're trying to do is create at research universities an academic environment that promotes and rewards innovation and creativity. In many respects, the traditional tenure system does not promote and reward innovation. It promotes and rewards people who follow a set of criteria. And at the major research universities, we're breaking down those barriers so that people who are creative, who think differently, get rewarded and promoted. We're also working closely to bring together a triangle of university, government, and industry. That is critical to the output component of what we do in terms of doing things that are good for society. The United States has a unique ecosystem for doing that. In fact, if you look at the rankings of world universities, the United States populates almost all of the slots in the top 100 or so because of the unique way that we couple the education, the research, the service, and also government and university and industry activities. And that is very important, and we should not neglect that as we go forward. People always ask me, now that I'm the vice president for research, well, what's the next big thing? You know, what's the really coming technology we should focus on? And, you know, I used to give an answer like nanobiotechnology, but it occurred to me that the actual answer has not really changed for thousands of years. What's important are two things. There's the metaphysical question of where we are in the universe and to explain the universe about us. And there's also the physical world. And what really people care about in terms of research is how it impacts a very small number of things. Water, healthcare, energy, environment, food, information, infrastructure, transportation, and security. So all technologies that we work on are only important if they actually produce output which impacts one of those things that I just mentioned. So at the University of Maryland, we are very much focused on these important fundamentals in connecting education, research, and service. And we have had a strong record of training NASA astronauts. In fact, 2 of our graduates gave their lives for NASA and their country. William McCool, computer science graduate, was the pilot of the Columbia Space Shuttle, and Judith Resnick was a mission specialist on Challenger. So our students have really done a great job for their country and represented their university very well. So thank you very much.
Thank you, Pat. So as our next speaker, we have Dr. David Barb, who's the Executive Director of the Maryland Technology Enterprise Institute. And David has a varied background, starting in industry in what's Westinghouse up the road at BW Parkway. He worked at the NRL, the Naval Research Lab, also at the Office of the Secretary of the Navy, before he joined the University of Maryland. The thing that he seemed to be most proud of when I spoke to him is the fact that he wrote an invited paper for IEEE a number of years ago on a technology that can be found everywhere, and I mean everywhere. In fact, in this room, just about every one of us has a cell phone or an iPad or a computer with these CCDs. David helped write a paper that it was considered by many that were starting up in the industry decades ago on CCDs as the founding paper, almost the Bible of CCDs. Now, David is going to be talking about what novel techniques he uses to help foster innovation or help inspire more innovation in entrepreneurs.
Thank you, and good morning. So I think we can pretty much all agree that there's a great amount of technology that's being developed in university research labs and in governmental research labs, but not enough of it is getting into products and services for the benefit of society. From my perspective, I think there's some basic elements of a formula for innovation, and those elements would be the following. First of all, emphasize entrepreneurship in engineering and science schools and also in government research labs. From a university point of view, I think the mission of the university should be broadened from research and education to research, education, entrepreneurship, and innovation. We need more technologists who understand the basic entrepreneurship processes. Secondly, I think we need to introduce entrepreneurship to students at a very early age. Based on our experience at the University of Maryland, we know it works down to 8th graders. And I think that it can even work at an earlier age. So we need to develop a cadre of students who will become successful entrepreneurs. And I might say, maybe with a little exaggeration, I think it's never too early to start educating students, young students, about entrepreneurship. And I was very happy to see the hands-on demonstration in the NASA video, because I think the way to introduce students to entrepreneurship is through hands-on experiential processes rather than theory. I think the third thing we need to do is to develop a continuum of programs and activities to develop and support technology-based startups from our research labs. We need to identify opportunities. We identify problems that turn into opportunities in our research labs. We need to create an intensive short-term support for those startups. Sometimes people call that an accelerator. And we need a longer-term incubation and mentoring process, because you really need to stick with these startup companies for some period of time in order for them to be successful. And finally, it's very important that these support services be very near as possible to the sources of innovation. Fourth, I think we need to create incentives to bring researchers who develop technologies and companies that want to pull the technologies out of these research labs together to create new and improved products and services. And finally, I think there are plenty of models for doing these things that have proven to work and had really excellent results. And I think rather than waiting for somebody to develop a silver bullet, I think that's what we're doing. We're kind of waiting for somebody to have a silver bullet for innovation. I think the basic processes of doing innovation that I've mentioned before exist. It's a matter of adapting and adopting them to your own processes. So my closing words would be I think we need to follow the Nike slogan, that is, just do it. Thank you.
Great. Thank you, David. And rounding out our panel, we have our token scientist, but not just any token scientist. The title that was provided to us about Dr. Ralph McNutt, that he's a physicist, a member of the principal professional staff at Johns Hopkins University's Applied Physics Laboratory. But I don't think that is deserving enough. What's more important, I think, he's a project scientist for a number of really critical missions for NASA. including Messenger that's at Mercury right now or flying by, just flew by. But he's also explored all areas of our solar system. He's had his hands on as a co-eye for the New Horizons mission, Voyager, and Cassini. So he's really explored from edge to edge of our solar system. When I was asking him about some most noteworthy accomplishments or things he's involved in, he sent me a whole slew of MPEG files and all kinds of documents he's generated, and was absolutely impressive. But one thing that really struck me is trying to reach out to school students to help define a whole new mission called the Innovative Interstellar Explorer, where we want to go explore, have a mission concept to explore the interstellar space beyond our solar system. And with that, he's trying to see the imagination, the creativity, and inspire youth to engage in this exploration endeavor that we're undertaking. Today, he's going to talk about the importance of innovation for enabling science missions and scientific research.
Thanks, Peter. Well, it's a pleasure to be here and to be able to have this audience and to talk a little bit with you about what we're doing with innovation and technology in the part of the science missions that NASA carries out. Certainly, if it weren't for the fact that we have technology and a lot of innovation, most of these missions that we've been running around the solar system with simply would not exist, because when you're actually sending out spacecraft to try to make measurements that no one's made before, and sometimes learning things that you didn't even know to ask the questions about, it really is a question of where that the rubber hits the road. You have to somehow worry about not only what sort of science questions you want to answer and address, but what kind of measurements you need to make, how do I turn that into hardware, and then perhaps most importantly, how in the world do I package that within the mass and the power and the available launch vehicles and, oh yes, the money that is available for actually carrying these missions out. One of the things that NASA does incredibly well is to promote innovation through competition. There's the Discovery and the New Frontiers and Explorer lines of competed missions that NASA has. Science teams can go out and actually compete. The best idea wins, and you've got a chance to actually go prove that you can go out and do some exploring of the cosmos. I should say that I got involved with all of this back when I was 9 years old, watching Gus Grissom go up on the second suborbital flight. And then I guess it was in '62, of course, John Glenn made his orbital trip around the Earth. That was also the year that Mariner 2, that was the first successful U.S. interplanetary mission, flew by Venus. And I've still got that article from the newspaper in my scrapbook at home, and I was hooked. It was a real pleasure to be able to get involved with the Voyager project when I was a graduate student. I actually was able to go out with some of the engineers to do vibration testing on that out at JPL with one of the units that's on Voyager 1, which is now 10 billion miles from Earth. That's a little more than 12 light hours out. And of course, Voyager, which was launched the two Voyagers launched almost 34 years ago, will be by the end of this month, they're still working. And of course, this gets a little bit back to some of the things we were saying earlier about one of the issues that I think NASA has is to try to figure out how to reach out and tell more people about what's going on. I mean, this is, talk about innovative technology. Originally, when the Grand Tour was dreamed up by a graduate student named Gary Flandreau back in the mid-'60s, the real problem was figuring out how in the world that you could make a spacecraft last for 12 years. And the original concept for the Grand Tour mission was canceled, and everybody was told to go back to the drawing board to come up with a modest mission that would only had the requirement of lasting for 5 years, and that's what turned into the Voyagers. And of course, the spectacular success gave us our first clear view of the outer part of the solar system, but some of the instruments on board are still working. And every week they're sending back data on how that the outer part of the solar wind actually interacts with the interstellar medium. And the mission that Peter was referring to that I've been pushing on would be the one that would take over from that one. In terms of innovation, again, when you go to some place you haven't been before, you really have to think things through. And that's one of the reasons that you need the best and the brightest to be in this business. Messenger was mentioned. We launched back in 2004. It was actually originally conceived as a discovery proposal back in 1996. We went through the proposal process twice, approved for development back in 2000, launched in 2004, and we've now been in orbit about Mercury. First time that a spacecraft has been in orbit about the innermost planet. A spacecraft built here in Maryland, by the way. And we've taken over 40,000 photos of the planet. We're putting together a map. In terms of really innovative technologies, one of the things that's on board Messenger is a gamma ray spectrometer, which we are using to understand for the first time what Mercury is really made out of. And we've already made some rather interesting discoveries about how that Mercury is very definitely not like the Moon and much more like the other terrestrial planets in the solar system. The only way we were able to make that work was in order to have a cryogenically cooled detector. So there's actually a cryo cooler that is about the size of a Coca-Cola can, which is currently running on this mission in orbit around the hottest planet in the solar system and driving the detector temperature down to 90 degrees Kelvin, 90 degrees above absolute zero. And that's what makes it work. There is no backup. When we originally were putting this together, there was very limited flight information on what you could do with these. This was a cooler that was originally developed for flying on air-to-air missiles. Didn't have to work for that long in that particular application. As far as anybody knew, the mean lifetime for it to function was something like 1 year plus or minus 1.5 years. And so, you know, talk about innovative. We ended up actually getting involved not only with the makers of that particular cooler came out of Israel, but also we had colleagues at the Department of Energy at Lawrence Berkeley National Lab and Lawrence Livermore National Laboratory who aided us in order to put the whole package together with the thermal design. And that being able to do that with that sort of innovation on the fly has actually opened up a whole new chapter in what we're learning and what we're understanding about the inner part of the solar system. And let me just close with one more example. One of the things that's currently under development is a new probe, a thing called Solar Probe Plus. It's just in the beginning. And if you thought Messenger was hard, and I've told this to the engineers before, this one gets even more interesting. We've of course known about the solar wind that is the medium by which that the sun affects lots of things that go along in our technological society on the surface of the Earth, from BlackBerry reception all the way to satellites working. And we first discovered that the solar wind really did exist with the Mariner 2 measurements back in '62. It had been predicted theoretically by Gene Parker, physicist at the University of Chicago back in the late 50s. But the problem is we still don't understand the physics of how exactly that the sun makes the solar wind and why that the corona is so hot. So for the last 50 years, the scientific community has wanted to try to send a probe into the outer atmosphere of the sun. And one of the things that the Science Mission Directorate has got going right now are studies for actually building that spacecraft. And there's been a selection of instruments, and hopefully things will carry on. We're hoping for a launch in 2018 with a mission running till 2026. And it gets back to getting a lot of people out there that might think that they're interested in science to go ahead and start working on honing your math skills and your English skills, because we're going to be needing you to help to analyze that data, and perhaps a little later with some data from the Interstellar Explorer.
Great.
Back to you.
Thank you, Ra. So, David?
Thank you to our panel. We'll now take questions from here in the audience and also from our followers on Twitter. If you have questions for the panelists and you're following us on Twitter, please send them to our @NASA_technology Twitter account, and we'll try and get them up here to the panel. And if you have questions here in the audience, please come up to the microphones. They're in the aisle so that we can hear your questions and our viewers on NASA TV can hear them. Sir?
Hi, Joe Rivera, the Chief Technology Officer for Abacus Technology. I wanted to expand a little bit on some of the stuff that Jennifer was saying and also Dr. Barbie, in that, a lot of times as a fellow academic, we tend to focus on the getting the PhD, getting the master's, getting the bachelor's, but we tend to forget that real creativity and real innovation is born of pain. It's born of rejection. It's born of rejection by peers, rejection of the norm. Look at Michael Dell, Bill Gates, Michelangelo, Lady Gaga. Read anything about their personal history, you realize that they were creative, innovative because they were rejected. They were felt pain. We need to tap that market. Get into those folks that say, hey, look, we realize you may not be the sharpest crayon in the drawer, but we know that you have some pain. Let's tap into that creativity by not rejecting that little form of diversity, not just focusing on the academics, but focusing on those people and trying to bring out that creativity of saying, just because you feel like you're being rejected, just because you feel like you have pain, use that to propel yourself to find that creativity, to find that innovation. Just a different market we need to tap into.
Comments, panel?
Well, I'll say that that's very difficult to do. I think it's something that we have to take that challenge on, because if you think about Einstein, right, and the example of how his inability to really grasp the concept of the temporal nature of things, that was a frustration, right? That was not something easy, and yet look what came out of it. As a leader, with 70,000 engineers roughly in the corporation, how do you make those people whose idea it wasn't feel valued and feel that their contribution really led to this better result? And how do you make that reward creative failures? Those are the kinds of things that it's not a geek thing, right? But as a leader in a technical world, those are the types of things that are really what we need to be focused on as well. Yeah, so yes, like gigabit comm, yes, multiple aperture optics, lots of other technology, but sometimes we've proven as a society that if we look at technology and say, I want to improve the technology readiness level of this technology, we've proven we're able to do that. To David's point, what we sometimes have not been able to do is transition that technology into a compelling application that changes lives, as Joe was talking about. So I think it's really an important subject. I'm glad that we focused on it.
If I could just mention one other thing. I think that's fascinating, that innovation stems from a fundamental dissatisfaction with the status quo. And if you're satisfied with the status quo and everything is going fine, you're not interested in change. So the greatest innovators are the ones that are standing in the back going, I don't like that. I want something else. And we, part of society is everyone trying to work together. And sometimes it's the person who's in the back throwing rocks, who's the one who's really going to change things for the better for the rest of us who are inside the box. So how do we make the most out of that creative dissonance is a fascinating aspect of innovation.
More hands-on events, more types of things like that. I think that's spurs the creativity.
Right. We just need you to use the microphone, please.
David, did you want to comment?
So a couple of comments. One of the most difficult things I find in teaching entrepreneurship classes is letting the students know that entrepreneurship, by its very nature, you have to learn how to manage risk, because if you look at successful entrepreneurs, typically they've failed a time or two before they succeed. So they have to be able to, if you're too risk averse, you're probably not going to be a good entrepreneur, okay? And secondly, what entrepreneurs do is they look for problems because they know a problem equals an opportunity.
I like to tell my students that it's important that they experience failure. We tend to reward students for unbroken success. In fact, we do the same with faculty. But as somebody famous once said, failure is the fuel of success. And somebody else said that success is not the lack of failure. I tell the students there are 6 phases. There's frustration, fear of failure, actual failure, followed by serendipity, surprise, and success. And that's what all explorers go through, right? Lack of funding, underfunded project, you set off, you get lost, and then you find the Bahamas when you were looking for China, and you make success out of that. Okay, so we've got to encourage that in our students and our faculty. I think it's very important. I had a student come see me who had a 4.0, and I was about to give him a B, and he thought his life was over because he was going to get a 3.95. I told him this would be the most important thing in your life, actually, to get a 3.95. You'd be a better person for it.
Again, if you have any questions, please come up to the microphones. Our panel is available to take your questions here or via Twitter at the @NASA_technology account.
I kind of have a comment. And this is to Joe Parrish. The SBIR, STGR program is a very important program for NASA and other government agencies to fund early stage innovation. And when it's discussed, a lot of times it's talked about in terms of SBIR, but there's the university component, STTR, where universities can partner with or even propose on their own, innovative technology. And my company is very involved in this, and we just started getting more involved with the STTR and partnering with universities because I see them as real sources of innovation, and as a research-focused institution, their job isn't really to commercialize things. They may teach classes in entrepreneurship, but there's a point at which the university's responsibility ends and the students have to go on and become the entrepreneurs that they may be or maybe not. Many people aren't aware that this program is about, 60 days from needing to be reauthorized again, and it narrowly passed, got an extension to September 30th. And I just wanted to know what Joe and others at NASA are doing to ensure that this program continues in the future. And I wanted to ask, Dr. OShea and Dr. Barbie, what are you guys doing at the university level to, I'd like to see students go through the SBIR RFP and come up with ideas that, I traditionally have to go through the department and the professors, but they have all these other things that they're doing, and I think there's a lot of young people here who have great ideas that if they look through the topic lists and they thought, I have an idea, if I could just get connected with someone who would like to partner with me, I'll promote it to my professor and then we'll go do these things. So be more proactive in that. So, thanks.
Great. Thank you very much. The SBIR STTR program is one of my very favorite topics, so you merely push the button. A couple of facts and a couple of thoughts in relation to the issue of reauthorization and also what the proper balance is between academia and industry and participation in STTR in particular. First of all, the SBIR program at NASA, at least, is a fundamental component of our overall research and development portfolio. Right now, the SBIR program at NASA is approximately a $175 million program and represents a very sizable fraction of the overall R&D funding that's available to us within the Office of the Chief Technologist. And we then take the SBIR program and apply SBIR research to the benefit of the various mission directorates within NASA and also look to commercializing those developed technologies outside of NASA. So it's endemic throughout NASA's R&D program, the contributions that are being provided through SBIR and STTR. You're also quite correct that we're going through a reauthorization phase within Congress and that the SBIR program, there are some very innovative ideas for new elements to the SBIR program There are some differences between the House and the Senate on some of the finer details of the proper role of participation of venture capital firms and some other elements of the program, but there is universal bipartisan support for the notion that small businesses and their research partners, particularly in research institutions, are an incredible economic innovation engine for technology development that can both serve internal needs within the various agencies that participate in the program and outside through commercialization. Just one last quick note about the proper roles of the research institutions and the small businesses in STTR. I've had the great pleasure of being associated with a number of STTR projects at a sort of personal level, and I've also had the opportunity to observe the way in which these projects influence R&D development within NASA. And I've noticed that the ones that are the most successful are the ones that tap the true creative energy that you have in the academic institutions and research institutions. They're where the really brilliant ideas come from, the fundamental kernel ideas come from. And then the small businesses are fantastic at being able to package these ideas into technically realizable prototypes and other ways that can be adopted. And each of these entities play kind of a unique role, but a very complementary one. So when you have that partnership between the idea factory and the people who can take that idea and apply the proper shaping and sculpting to that idea to make it real, then you really have something. And so that's one of the fundamental tenets of the STTR program, and I think it's fantastic. So thanks for the opportunity to talk about it.
I just want to add, we're seeing a change in leadership for SBIR program under Joe, and we have a new director of the program, Rich Leshner, out at headquarters. I just introduced myself yesterday, and he's really open to new ideas. So those of you in the Maryland community, if you want to reach out to me at Goddard and funnel your ideas to me and through Joe or in conjunction with Rich, I'd be very open to that. Because I take SBIR very seriously. It's very important that the Goddard portfolio, I work closely with the subtopic managers, make sure they are strategic, make sure we are making selections that are vital to our future and that are going to have an impact.
So I totally agree with your comment about the value of STTR and SBIR programs. I think it has done the country a lot of good. However, I would take a little issue with your statement that the university responsibility ends when students graduate. I think it's true at most universities, but not at the University of Maryland. Through the organization that I direct, MTech, we have a number of programs that can help students and faculty start companies, and we'll work with them for years. And just let me mention a few. One of which is our Venture Accelerator program, where we identify the most likely commercializable technologies that come out of the research. And we will actually work with those students and faculty for a period up to 2 years to actually do market research, put together a business plan, bring in initial funding, introduce them to customers, and actually bring in management to take the company forward if necessary. We've also operated an on-campus incubator for 25 years. And from that incubator, we've graduated 95 companies. Two of which are billion-dollar companies that have been acquired in the last 2 years for over $1 billion. One of which was the company that developed the hybrid electric drive for Toyota and Ford automobiles. So we've done had some pretty significant successes out of that. We've also run a program called MIPS, Maryland Industrial Partnerships, where faculty and graduate students conduct projects on campus for Maryland companies to create new and improved products for those. It's basically market pull. And so through that program, we have helped companies in Maryland create products and services that have created revenues of $21.6 billion. Actually, if you look at the tax money coming in back into the state from that program, it more than pays for itself.
So we got a question through our Twitter account. I'd like to loft it up for the panelists to consider. The question was, innovation through competition is great and it's very successful, but what about innovation through the community? The idea of open source. Does anyone have any comments on open sourcing innovation and technology? What can make it work even more effectively? And other ideas how we can weave it into our innovation and technology focus?
Well, I can offer a few comments on that. I think open innovation is a great, and again, untapped resource. So if you think about collective intelligence, it has that aspect of diversity. And so when you throw out a challenge, I know NASA has some like grand challenge. When you throw that out and allow these diverse teams to work on that, you get the better solutions. And I think emerging technology that we're starting to use are things called prediction markets. And so if you look at prediction markets, it's really an idea market. You put a concept out there and people either say, yes, I believe this is going to happen, no, just like a stock market for concepts. And I think it's really powerful because it has the ability to very efficiently aggregate information that's coming, ideas that are coming from very diverse sources without ruining the diversity of that source. And I was able actually to convince us to try to do one internally, mostly because NASA did one in the clickworkers experiment. I don't know how many people are familiar with that, but it was a very interesting thing where there was so much imagery, and somebody else might want to talk about it. I'll say what I think it is. So much imagery coming down that it couldn't be exploited by the on-site experts. So you turned it over to anybody in the world with a little bit of training. They were able to put these measurements in of craters, I believe it was, and through aggregating multiple sources of that, you got good solutions. And so I think that that's the kind of thing, those types of open source innovation enabled really by our ever-evolving information technology capabilities.
I like the idea of combining competition with open source solutions. It's good when there's a reward at the end, and a good example of that was the DARPA Red Balloon project of a couple of years ago, where DARPA put up a dozen or so balloons at random locations around the country, and the competition was who could figure out where they all were in the shortest possible time, which induced a lot of competition-based open source creativity and innovation.
There's you may be aware that there's a company in California called IDEO. And IDEO uses a similar process where typically large companies come to IDEO and they say, we need a new product or an improved product developed. So they give them sort of very broad specifications. And IDEO brings in a group, extremely diverse group of individuals. I mean, maybe psychologists, engineers, you name it. And through a series of processes, they narrow down to the most innovative solution to that question that the larger company has asked.
Okay, thank you. We'll take one more question from here in the audience and then wrap up the panel. Sir?
I would like to underscore your experience with the ClickWorker program, but my problem right now is I can't find where it went. I'd like to use it in my STEM outreach with Civil Air Patrol and other things. I can't find out where it actually is going to go and what future it has. So that's a question I keep putting to folks. But it was a very, very nice experience to actually work that and enjoy exploring bits of Mars or whatever the terrain happened to be. I think that's a very important notion of getting out into the cloud and exploiting synergies. But I'd like to ask again, when you folks really look at the details of how to make innovation happen, do you spend a lot of mental energy and spend some time thinking about the synergies between green energy technology and oil independence technology and exploration technology, and how can we really see leverage between those parts of our technology in a very, very real way? Can we see programs which invite really cross-disciplinary cooperation between agencies? You have to go across agencies to get this kind of thing. And can agencies, in fact, have sort of super SBIRs and super STTRs where the money is longer term and the targets are more broadly based, and there is this real imperative to say, look across all these problems, think out of the box, see how putting something on Mars is also helping you put something in somebody's garage. What do you think?
We're short on time, but I'll react to that, saying that I'm a big believer in the importance of reaching across disciplines, reaching across programs, reaching across agencies for new innovation. Not only at the program level from the top down, but also encouraging the innovators to always be aware of what's going on outside of their existing program, outside of their university, so they could identify new opportunities and areas where they can innovate even more. With that.
Okay, thank you. We're out of time for this panel, but I want to thank all of our panelists for their thoughts and appreciate your coming today. We're now going to move on to our next panel. Before we do, I'd just like to make a couple of housekeeping notes. Again, if you're watching and joining us on NASA television, you can watch us streamed on NASA TV Live on www.nasa.gov/NTV. If you're following today's conversation on Twitter, you can join in the conversation. Pound NASA Future, there we go. Again, you can follow us on Twitter using the pound NASA Future, or by sending your questions to our panelists through @NASA_technology. Following the next panel, we're going to take questions from the audience again. If you have questions for the panelists during the Q&A, we ask that you do use the microphones in the aisle so that our viewers on TV can hear your questions. After this panel, we'll be taking a break, brief lunch break, and then starting back up again later this afternoon from here at the University of Maryland in College Park at the Riggs Alumni Auditorium. Our next panel, as part of today's NASA Future Forum, is a panel titled Science and Discovery, Pushing the Limits of Knowledge to Inspire a New Generation, which will be led by Michelle Thaller, an astrophysicist and communications expert from NASA's Goddard Space Flight Center here in Greenbelt, Maryland. Michelle?
Thank you very much. Good morning, everybody. The idea of discovery, what really is coming in the future, what is next? It's difficult to imagine the world for me, for example, before the Hubble Space Telescope or before the Voyager missions. You know, can you remember, I was born in 1970, and I never had a chance to think of planetary science as just these distant little lights in the sky. They were always worlds to me. I grew up with that idea. In our panel today, we're going to talk a bit about the power of discovery. You know, what's next in the future? What do we see as some of the most important discoveries coming in our generation, in our lifetime? And to discuss this, and I'm hoping that this will be led mainly by your questions. I would really like this to be very collaborative. I understand we'll get questions from Twitter, whoever else is emailing us. But please, let's make this as collaborative as possible. We have some of the world leaders here to talk about where discovery may lead us. So not to waste time, let's go right ahead and have them introduce themselves and give a short introduction, and then we'll open up to your questions. Thank you.
So I'm Waleed Abdalati. I'm the chief scientist at NASA, which is a great gig, actually, because every day I'm totally blown away by something NASA's doing or other agencies, space agencies are doing that's phenomenal. And what I like about it, and what I think sort of has us all roped in, is that from the beginning of time, people have looked up and wondered. We've looked at stars, we've looked at planets, and have just been filled with questions about what they're like, how they came to be, what our place in the universe is. By looking outward, it prompts some very profound questions inwardly. And as our capabilities evolve, we actually have gone out there and been able to look back at our own Earth, which has triggered another set of questions about the planet we live on, how it functions, how it's changing, what it will look like in the future. And I just want to sort of plant a few seeds, because the main purpose of this is to be conversational. So I hope I'll trigger a few thoughts. What we do in science at NASA is unbelievable. It really is the stuff of dreams. And if you heard what I said in the beginning, our dreams are becoming our successes. We look to the edges of the universe and the beginning of time as we understand it, back very close to the Big Bang, over 13 billion years back into the past. We look at the planets, our celestial neighbors in the solar system, that are providing clues as to how we came to be, how the Earth has formed and evolved, and perhaps where it might be going. Just very basic questions about life, about survival, about evolution. We look at the sun in ways that are essentially impossible without going to or near it. And a lot of people think, the fundamental ingredient of life is plants. Life on Earth, human life is plants. I'll go one step further and say it's photons. Those plants turn photons into glucose that form the foundation of the food chain. So understanding the sun that fuels life on Earth is an incredible pursuit and undertaking. And finally, the planet we live on today, and perhaps more importantly, the planet our descendants will live on tomorrow. There is value to knowing what tomorrow will bring. It's important for our success as a species on this planet. And it looks like I skipped over in my notes. Well, when I talked about our celestial neighbors, I want to remind people, the prospect of liquid water on the surface of Mars, the prospect or the observation, as I said earlier, of methane raindrops on the surface of Titan, learning about the history of the solar system that's been erased by tectonics on our own planet by looking at things back 4.5 billion years to the start of our solar system. So deep space, beginning of time, our celestial neighbors, the sun that fuels us, our very own planet. I mean, what could be more important endeavors? So I find the science at NASA, as I said earlier, inspiring, and I find it of a great service to humankind. The tagline for the Office of the Chief Scientist is science to inspire and science to serve. There's a tremendous, beautiful, amazing, magnificent, magical universe out there, and as we peer out into it and go toward it and look back, I think the secrets we're revealing and will continue to reveal will blow us away and serve us all well. With that, I'll go back to Michelle.
Thank you. David.
Thank you, Michelle. I'm David Pierce, and I'm here this morning to represent the NASA's suborbital program. I would suggest to you that you cannot talk about Earth and space science discovery and innovation without also talking about NASA's suborbital program. Since the earliest days of the agency, NASA's sounding rockets, balloons, and aircraft have enabled discovery by, as what Waleed was talking about, working with researchers to take a dream, turn it into a prototype piece of hardware, fly it for the first time, and if it doesn't work, they go back, rebuild it, rework it, refly it until it's right before they put it on orbit. The mission of the suborbital program at NASA is simply to support science. We're like that German chemical company. We don't do the science, we make the science better. We enable the scientists at NASA to take that idea and to turn that experiment and that concept into detectors to make state-of-the-art measurements to validate models such as the ozone hole, or develop technologies that will become part of a spacecraft. Over the last 3 decades, over 6 instruments have been developed on NASA's aircraft, sounding rockets, and balloons that have gone on to fly on NASA spacecraft to do both Earth and space science. That's quite an accomplishment, and it's because the suborbital platform serves as a flying laboratory where both researchers and the students that work with them can experiment, try something new, collaborate with others, and work it out before it becomes part of a space mission. Instruments have a long history in NASA, and along the way of working on those instruments, we've also developed the next generation of scientists and engineers. In fact, it's one of the finest training grounds for innovation that we have in the agency, and probably one of the best kept secrets of the agency, is today's science leaders got their start in suborbital. One example would be a young scientist who was a graduate student at Berkeley, whose thesis was to measure the cosmic microwave background radiation. He had an idea of what they wanted to work on, but along the way he learned to solder and learned about optics, and he put his science payload together, and the first time he flew it, it didn't work. And so they took it back and they reworked it and reflew it. He graduated and got his doctoral thesis done, and then he went on to design the COBE mission. And of course, Dr. John Mather went on to accomplish much more, receiving the Nobel Prize for Physics in 2006. But it all started as a graduate student working on suborbital platforms. So anyway, I just suffice to say, we help enable science and innovation, and we help develop the next generation of scientists and engineers. Michelle?
I have to say, I was commenting to David this morning that one of the public misconceptions about NASA's suborbital program is that people don't often think that it is doing cutting-edge cosmology, for example. And some of the balloon missions that are going up right now are doing things like studying the polarization of the microwave background, looking for clues of pre-inflation physics. The depth of science that the suborbital program does is compelling and challenging to communicate to the public that that's the case. And so I think I'll go on then to Matt.
Thank you very much. I'm Matt Mountain. I run the Space Telescope Science Institute, which runs the science program for NASA for the Hubble Space Telescope. And when I tried to work out what I wanted to be in high school and then into graduate school, I couldn't work out whether I wanted to be a theoretical physicist, an astronomer, or a particle physicist, or an engineer or something. And I chose astronomy in the end because you could be all of the above. Because astronomy is a technologically led and drives technology as well. I mean, ever since Galileo lifted that telescope up 400 years ago, technology has defined the direction of modern astronomy and astrophysics. And it hasn't been more so than in space science. You know, it was in 1946, way before the space age, that Lyman Spitzer wrote a paper for something called the RAND project of the Boeing company, saying we need to have extraterrestrial telescopes because this is what you could do. Now, we all know, years later, it wasn't until 1990 that astronomers actually got that technology of the Hubble Space Telescope. But in the interim, that science fiction idea had been put to great use by other agencies. And the Hubble was, in fact, the fourth or fifth of those technologies. And look what's happened when we've taken those technologies and put them in the public domain. I mean, which discovery can you think of that hasn't come from the Hubble Space Telescope? You know, when do you get a New York Times editorial that writes, "It has taught us to see the properties of a universe humans have been able, for most of their history, to probe only with their thoughts"? That's a NASA mission, a science mission. Much more tangibly, at the Institute, we have teachers. We create curricula. All 50 states use the education program that flows from the Hubble Space Telescope. Half of the largest state departments of education recommend Hubble-inspired maths and reading programs for their curricula. Every year, 500,000 teachers use our programs. They touch 6 million kids a year. This is about science education, it's not about astronomy, because people are inspired by what they do. At the tertiary level, what does this mean? Well, the Hubble Space Telescope is a great science mission, but we also, over the course, have funded $300 million worth of young researcher funding in universities. And why is that important? Well, only 7% of those people, those postdocs, those undergrads, actually end up as faculty astronomers. So where do the 150 people every year go? They go into industry, they go into educators, PhD rocket scientists that wouldn't have been PhD rocket scientists going into the infrastructure of this country because of telescopes like the Hubble. So what about the future? Well, we're already working on the successor to the Hubble Space Telescope. It's called the James Webb Space Telescope, and it's been in the press a little bit recently. But it's an amazing telescope. It's the largest space telescope that's ever going to be flown. But the reason it's possible is because of a huge investment made in industry by other agencies and other parts of the government. We are benefiting from the ability to build extraordinarily large structures in space that can deploy, that are today used in the national defense era, and by actually commercial satellite providers to beam high-definition TV down to you and I. But what astronomy shows, and investing in these technologies proves, is that you also, to make these technologies do science, they have to reach even further to make something like the James Webb Space Telescope. We've had to take mirrors, 18 of them, made of beryllium, that are so smooth, if you took the mirror and you stretched it across the US, the largest bump on there would be about 2 inches across. These technologies can be used again and again, whether it be for detectors. And the James Webb Space Telescope, for the very first time, puts NASA in the pole position to lead. NASA now has the largest space telescope on the block. And other agencies will be looking at those technologies and thinking, what else can we do? How else can we actually use these technologies in the next 20, 30 years to actually benefit the nation, whether looking up or looking down? So what about the future? Looking beyond that. See, the James Webb Space Telescope, if you look at the broad stretch of science, as Waleed tried to point out, it's only a stepping stone to the ultimate question. Because what astronomy and astrophysics ultimately can tell you is that question that we as a species have yearned ever since we looked up at the sky, are we alone? We're on the verge. This generation is on the verge because of the technology investments NASA has made. NASA is uniquely positioned to answer that very fundamental question, are we alone? Because we've learned so much with NASA space telescopes. We know there are now thousands of planets out there. We know what's in their atmospheres. We know where all the stars are. So for the very first time in human history, because of the investments that NASA can make and has made, we could build telescopes which are even greater than the James Webb Space Telescope, that actually could answer that profound question. And think how transformational that would be. If you found life around another star, it would probably be as transformational as Copernicus and Darwin combined because of the investments NASA makes in these kind of technologies. Think of the kids that would be inspired, because for the very first time, they would know there's a Pandora out there that they could possibly get to. Suddenly kids begin to think about, how would I build a rocket to do that? What else would I understand? What biology do I need to know? What do I have to know about planets or climates? Maybe the discovery of life around another star would be as profound for the 21st century as Neil Armstrong's footsteps were to the 20th.
One thing that working at NASA sort of has us poised to do is take a little look over that hill, Matt, and you're talking about the possible discovery of life. I often say to children, that are in kindergarten, that, I would like by the time they are in graduate school, I would like there to be a solid example of life outside the Earth. Whether it's on Mars, especially with these saltwater flows that we're seeing, with the seasonal methane emission that's observed on Mars, or whether it's something that the James Webb Space Telescope finds, an oxygen line in a faraway planet's atmosphere. we really may be in the last generation not to know the answer to, is there life outside the Earth? That's really true. And I agree with you that this could be profoundly transformational, and we're just on the cusp of it.
And only NASA can do that.
Yes. Tony.
So good morning, everybody. My name is Tony Busalacchi, and I head up the Earth System Science Interdisciplinary Center here at the University of Maryland. Our center, ESSEC, is joint between NASA and NOAA. And prior to coming here to the University of Maryland in 2000, I was at the NASA Goddard Space Flight Center for 18 years as a civil servant. So my remarks this morning are going to be predicated on my experiences at NASA, here at the university, and also someone who delves a lot in sort of international environmental research. The whole field of Earth system science really owes its genesis to NASA, going back to the 1980s and the 1990s. And we talk about Earth system science, we are literally talking about how the Earth acts as a system, how the atmosphere, how the ocean, how the land surfaces couple together, how those component parts of the Earth system add up to give the puzzle, the fabric of life that we live on in this planet, how these individual components give rise to natural fluctuations, and then how has man's presence on this planet altered these natural fluctuations. And it's really only that perspective that space affords us, viewing from satellite platforms where the lens is turned back to our planet, that we can really appreciate how our planet acts as this integrated system. So it's this perspective from space that gives us this opportunity to study how our planet has changed in the past, how it's changing right now, and how it may change in the future. Now, this science goes back to the early 1960s with the first weather satellites, but the field has really gone much further beyond just meteorology to the broader atmospheric sciences and observations of atmospheric chemistry and aerosols, to oceanography, hydrology, cryospheric processes, observations and understanding of terrestrial ecosystems and marine ecosystems. So we're now able to look literally at the heartbeat of the planet on timescales from days to decades, the pulsing of life on the planet on these timescales, and now using that information to diagnose the planet we're living on and where things are changing. Where are the anomalies? Why are those anomalies there? And then what does it portend for the future of our species on this planet, and how we can use this information, not just for science, but for the protection of life and property, to inform policy decisions, to make wise investment decisions, and also in support of national security, where environmental perturbations around the world are often a threat multiplier to existing problems, as we've seen, for example, recently in Somalia. So this whole field of Earth system science goes back again, as I said at the beginning, to what was known in the 80s and 90s as Mission to Planet Earth, that then evolved into the Earth Observing System. And EOS, as it's known, I would argue was a successful, very successful proof of concept. And it was a proof of concept. And one of the pressing questions is, what will be its legacy? Will this approach to monitoring the Earth as a system succumb or be a victim of its own success? Or will it be a trailblazer to the future in support of all those different sectors? And I hope we can delve into that a little bit more.
Just one short comment. One of the things that I'm able to do at Goddard is often talk to embassy staff from all over the world, as well as congressional visits that come to Goddard. And the idea that NASA is a world treasure when it comes to Earth science, as Tony was talking, the breadth of ways that we observe the Earth, everything from disaster relief, the gravity recovery and climate experiment was able to record crustal shifting under Fukushima after the earthquake and tsunami. We are a world treasure. This data is available to any nation's government, any person on the planet for free. This is something that our nation needs to be extremely proud of. There is nobody else providing this service right now. And it is the most important time, perhaps, in human history for us to be monitoring what the Earth is doing. Now, I don't think it was deliberate, but Tony is actually a bit of a NASA person and a NOAA person, and so we have sort of NASA on this side, and we're going to end then with NOAA. So please.
Okay. All right, thank you, Michelle. I'm Dave Novak, and I'm coming to you from the National Weather Service. We provide the nation's fundamental weather and water information to save life and property and enhance the economy. I'm in a sub-agency of the National Weather Service, the National Centers for Environmental Prediction. And you may have heard of the National Hurricane Center or the Storms Prediction Center. I'm located in the Hydrometeorological Prediction Center, where our focus is on heavy rainfall and heavy snowstorms, as well as extended forecasts. I want to mention some key partnerships. NASA has been critical to the weather enterprise in terms of advancing our science. Weather and meteorology is really an application of some of the NASA science. Certainly our first view of Earth from space was revealing to us from meteorologists as we could see these weather systems as they move and in their entirety. So we're really excited to be moving to our new location, just a stone's throw away here at the M-Square Research Park, where we'll be in closer connection with the research community, such as here at University of Maryland, as well as NASA Goddard, to really take advantage of some of the NASA science, as well as what the academic community is doing. Now, one of the questions Michelle had challenged us with is, why does your science discipline matter? And if I could have a show of hands here, how many of you either heard or saw a weather forecast this morning? Right. I mean, weather is pervasive in our society. In fact, a recent estimate has noted that among America's weather industries, about $500 billion is sensitive to even mundane weather events, rainfall, snowfall, cooler than average, warmer than average. And then if you turn attention to extreme weather events, which we've certainly seen many this year, ranging from floods to droughts, tornadoes, hurricanes, you really see the incredible loss of life as well as threats to the economy from these weather systems. And so as a scientist, being able to see how science is applied in a very practical way to make weather forecasts that impact everyone in this room, save lives, enhance the economy, is really inspirational and rewarding. Now, you've probably heard many weather jokes, and I have, of course, myself. For example, we're the only profession to get paid to be Ron. But if you think back from where we've come from, here in the DC area, of course, a snowstorm can be crippling. And if you think back to your childhood forecast of a snowstorm here in the DC area, and you compare that to the forecast you're receiving today, airlines are canceling flights 2 days in advance. It's sunny, it's calm, but they're canceling flights on forecasts that NOAA's providing, and the event happens. And so this is really, for the entire scientific community, this is really an accomplishment. Of course, we have a long way to go. There's no question about that. And so the National Weather Service recently came out with our strategic plan for 2020. And in this plan, our goal is to make the nation weather ready, building a weather ready nation. Now, a key component of this is building upon the science and technology that we have to make our forecasts even more accurate than what they currently are. But we've recognized that just making a good forecast, it's not enough. As we've seen with a number of extreme events, you have to have individuals take action. They have to understand the message, understand the scientific information that they're receiving. And so it's communication, it's a sociology and a behavioral science issue. So it involves interdisciplinary science aspects that NOAA and the National Weather Service are certainly getting into. And I'll just briefly mention another aspect of that plan is the recognition of the need to include confidence in our forecast. to recognize that the Earth system is incredibly complex, it's chaotic, and that there is uncertainty in our forecasts and projections that go out, and to acknowledge that and to actually build that into our decisions. So finally, I just want to close that we all recognize it's a very tough budget environment, and yet the need for environmental information is rapidly growing. And so I think the challenge as we look towards the future here is we know that it's even more important for new technology, new science, and new innovative ways of thinking about how we can tie science and technology together to address these critical environmental issues as we are budget constrained. So I look forward to your questions as we continue to think about the future.
Well, thank you. We already are getting some questions from Twitter, but I want to make sure we also, I'm happy to get to those. I'd like to give people a chance here. We have a wide range of panelists. I mean, I can think of a few questions I want to ask everybody, but maybe should we open it up, or shall I start with the Twitter? Or?
I was just going to invite folks here in the room to come up to the microphones if you have questions for our panels. We have microphones here in the aisles if you'd like to come up and ask a question for anyone on the panel. We also do have some questions from Twitter.
Yes,
so if you want to start out with those, we can. And if you want to come up to the mics, why don't we start with one here at the microphone and go to Twitter.
Sounds
Sir?
good.
Yes, hi, I'm Greg Schuckman from the University of Central Florida. I'm reminded of a quote by a member of Congress saying, why do we need NASA and NOAA to do the weather monitoring? Because we have the Weather Channel.
So, I have heard this. It is such a brilliant quote. Does anybody know who said that?
I don't think they're owning up to it, whoever said it.
So the question really is, and by the way, thank you for the panel. It's really wonderful and inspiring, and I have a 9-year-old son at home that would have loved to hear all this because he is very inspired by the work that you're doing and talking about. There was a GAO report not too long ago that talked about duplication of programs, and so I'm thinking about the programs that you have at NASA, the programs that you have at NOAA. USGS has a program as well that helps inform when you're talking about flights and volcanic eruptions and how that disrupts schedules. So I was just wondering, because I do support the work that you're doing and I think it is vitally important, but is there an opportunity to perhaps consolidate, coordinate better between the agencies so that there isn't the criticisms that are lobbed about duplicative programming?
So the answer is yes, and actually OSTP is working on that right now. There's a stack of Academy documents that are calling for, as in the GAO report, that we sorely need a national strategy for sustained space-based observations of the planet we live on that's inclusive of this aspect of roles and responsibilities across the agencies, dealing with issues of cost growth, mission creep, access to space. So OSTP is working on that right now, and I'll also be a little bit parochial. David alluded to it. Here at the University of Maryland, with NOAA moving onto campus with 800 plus civil servants, with Goddard down the road, we have arguably the largest collection of earth scientists in this 5-mile radius anywhere in the world. That means we have the responsibility. We have the responsibility to help take on this problem and provide some solutions. So I'm actually not very sanguine in the midterm about this, but in the long term, I'm extremely optimistic that with the talent here and the agencies here, we are going to tackle this problem and sustain these observations in the long term. And a lot of us are very anxious to see what OSTP comes up with.
Yeah, I'd also like to add, I fully agree with everything Tony said. There's one thing to add to that, though, is I think some of that perception is a result of not being fully informed in what the current roles and responsibilities of each organization are. There is certainly room, I think, for optimization, but at the same time, I don't think there's as much redundancy as some people may think, because NASA is a research and development organization. We figure out how to do it. NOAA takes that capability and turns that into useful and actionable information. So there are clear roles and responsibilities, and it's natural that there'd be not just a perfect butting up, but but in fact a little bit of overlap. So what OSTP is doing and those involved is trying to find the optimum.
I mean, I would just add, I mean, I fully agree with what Waleed said. It's not the redundancy issue as much as how do we sustain the enterprise? How do we cross the valley of death? How do we make the transition from research to operations? But here, because this is a critical difference from space science. We're talking about long-term sustained observations. How do we insert technology? How do we have stable and continuous observations? So it's not just discovery unto itself, but then it's going into the operational phase. And how do you do that where it's affordable? That's all part and parcel of developing the strategy, and less about the redundancies and how do you make this affordable and sustainable.
And I'll just briefly mention that I think the degree of collaboration amongst the federal agencies is really, at a high right now. So I think there's already been positive movement in that regard.
Super. Thank you.
Would you like to go to the Twitter question? All right. So I think this will definitely, I'll probably shoot this to Matt first and Waleed as well. As Matt mentioned, I think you set us up for the fact that JWST has been in the news a lot lately. And so we have actually a number of people that have asked, what is the status of JWST? And the follow-up is, what is at stake if it is canceled?
I'm sorry, what?
What is at stake if it is canceled?
If JWST is canceled, space science is at stake because it is the pinnacle of what everybody wanted to do for 2 decadal surveys. When you look at what the Hubble has done, the other space telescopes have done, what they do on the ground, the fundamental questions you want to ask is, what were the first galaxies? Is there water on other planets? There's only one way to do that, and that's with a telescope of that scale. And it was an investment that NASA is making and needs to make if we ever want to answer those kind of profound questions. It's the success of the Hubble Space Telescope. There's a generation out there that grew up with the Hubble Space Telescope and want to know, where's their Hubble? This is Hubble 2.0. We touch 10,000 astronomers, 6 million kids a year with our Hubble programs. We've got to sustain that engagement and excitement, not just from a scientific perspective, but from an inspirational perspective. And the important part of this is to realize that the James Webb is just a stepping stone to a much grander quest of, are we alone? What other technologies will we need over the course of the next 10, 20, 30 years to be that generation for the first time in our species history to answer the question, are we alone? And how do you inspire people to actually get into technology, into science? You give them important questions that only they think they can answer. How to build these amazing telescopes or construct them in ways that we could only have imagined. Think back to Lyman Spitzer in 1946 saying, I think I need a telescope in space. If he hadn't asked that question, we wouldn't have had the Hubble, we wouldn't have had the profound change in our worldview that has come about from putting telescopes in space.
I actually think I'll leave it at that. Very powerful. Enough said.
I know some of the inspiring things that I've heard from you, Waleed, do actually get at the heart of how expensive is this? How much of an investment is this for a nation? And just isn't this an incredibly cost-effective thing to do for the discovery that's going to come out?
Absolutely, and I think with all the amazing discoveries that Hubble has produced, we forget what it cost, what it overran, the fact that the polishing of the mirrors left us with a bit of a problem that needed heroic repairs that really showed, I think, the best of human spaceflight and science working together. We forget that, and we think about the amazing things it does, the children it's touched, the adults it's touched, the spirit deep inside us that images of the various nebulae, for example, awaken. You cannot put a price on that, and even if you could, you'd have to add to that the value that comes with the technological advances, leadership in the world in this particular area, the kinds of jobs it created, how many states have businesses that contributed to Hubble, that are contributing to JWST. So it on multiple fronts, it is a wonderful pursuit, worthy of the challenge, worthy of overcoming the challenges that we face.
Whenever I'm feeling a little bit down about the status of JWST and the arguments, there's actually a YouTube video that has nothing to do with NASA, entirely independent. If you do a YouTube search on JWST awesome, if it doesn't make you laugh, you should check your pulse, I think. It's a wonderful video done by some independent people, and just I think they really get to the heart of some of the exciting issues about JWST. I notice we have a question in the audience.
Yeah. Hi, my name's Taylor Hamilton. I'm a student here at University of Maryland. It's kind of a follow-up to the previous question. You talked about how inspirational the Hubble Space Telescope has been. How can NASA get the general public excited for the James Webb Space Telescope?
Well, what is quite interesting is that I give talks around the country about Hubble and so forth, and I put in maybe a few slides about James Webb. These days, and this is before the current action in the House, I get more questions from people of your generation about the James Webb Space Telescope than any other. When you see this transformer telescope, and it's the natural question is what's after the Hubble? What's coming next? Everybody knows after the last shuttle program, there is no way back to repair the Hubble Space Telescope. I mean, what people don't probably have missed is that 5 billion impressions, that's, people logged on or read an article, 5 billion people did this during the servicing mission, watch the astronauts fix the Hubble Space Telescope. And so people ask, and so I think the story you have to tell is the true story. This is a story of discovery. It's not a story about, well, these technologies will flow into industry and all these kind of things. That will happen naturally. But what people are inspired by is the fact that we can probe to the edge of the universe or look for liquid water on a planet around another star. This is our time. This is our generation. We will look back in 400 or 500 years' time and said, this was the generation that answered that question, we are no longer alone, or perhaps we are alone.
Thank you.
Hi, I'm Chuck Devine. I'm probably one of the very few polymaths in the audience. Anyhow, Michelle, I liked your introduction with the idea of having this being driven by questions from the audience very much. I also have to note that this is a 1 hour long session. You made that statement around 11:20 by my watch. The panelist statements, which were sometimes very interesting, ran until 11:52 by my watch. Is there any plan to actually have any sort of follow-up on this so that we can have a more lengthy and more in-depth discussion, obviously after this is over?
Well, we know that we're up against lunch, and I understand that's a powerful thing. 11:20 is when they've asked us to end the session, but I know that I don't need to leave immediately, and I think that, I don't know about my fellow panelists, but they may be around afterwards for more lengthy discussions.
Well, I'll certainly be around, and from my standpoint, our website, www.nasa.gov/chief-scientist, is how you can access us. And I invite one-on-one dialogue, multiple dialogue, any kind of follow-up, because we need ideas. We need to know your thoughts. What works? What reaches people? What stimulates the imagination? We all know in this room the amazing things we do. Carrying that outward, gaining or generating the appropriate appreciation for that is a dialogue I'm happy to have with anyone at any time in any forum. And I'll stay as long as anyone wants.
I've got a flight to Chicago to catch, but I'll stay until then, so.
I have a meeting I'd love to miss.
I believe we have another question from the audience.
My name is D.K. Sachdev. I'm from Spacetell Consultancy, a small company I started 10 years ago, and I also teach at George Mason University. Ever since Gemini spacecraft or before, NASA has been monitoring the health of astronauts, whether in a space capsule or a space station or on the moon. There are all kinds of technologies underlying that, I'm sure. Today we have a healthcare cost crisis, and many senior citizens like me who have more and more need for health checkups frequently, either for themselves or their spouses, still have to go to the doctor, wait for an hour to get some blood pressure checked. and things like that and come back and drive another hour. Why is it that the remote health monitoring technology which NASA pioneered more than 50 years ago is still not a viable commercial facility where simple tests can be done by remote equipment, transmitted to the doctor so that they don't have to travel and perhaps reduce the overall cost?
Well, I think there's sort of two steps in that. One, in your doctor's office, you are seeing the products of NASA investment. You are seeing, you know, EKG capabilities and CAT scans and you know, some very sophisticated physics that help us understand the human body and associated ailments or challenges. What you're referring to, if I understand correctly, is remote monitoring where you could strap something onto yourself and transmit, you know, your blood sugar levels or your cholesterol or your heart rate or any of that. I don't know the answer to that, except to say that I believe if it were viewed as profitable, industry would be all over it, and the capability is there. Turning that into a successful business model is something I don't know that anyone on the panel has enough expertise to comment on. All I will say is that when NASA investments in technology have produced capabilities for which there was a recognized market, they have flowed into the market. So if it's not in the market yet, it's either that it's not viewed as being commercially profitable, or no one has thought of it yet. So perhaps you can pursue some entrepreneurial endeavors and make that happen.
Thank you.
I'd also point out that after the lunch break, we're going to be having a panel that is going to be talking about technology investments and benefits and transferring technology. That's at 1:30, and they may have some experts on that panel that could also address that question. Another question from here in the audience?
Yes. My name is Joe Fuller. I'm the CEO of Futron Corporation, and I guess I have a question for the Chief Scientist. Notice the title of the panel is Science and Discovery, but there's no one on here from human spaceflight or exploration, human spaceflight exploration. And it seemed to be, there are like three NASAs. You got space sciences, you got human spaceflight, and you got aeronautics. As chief scientist, how do you bring these together? Because I don't believe that that's separated.
Yeah, absolutely, and that is a great question, and thank you for it. We don't have the full representation of science disciplines here. Frankly, we don't have a planetary scientist on the panel as well. But one of the reasons I was brought on, that the administrator reestablished the Office of the Chief Scientist, was a recognition that not all of the science in the agency falls under the Science Mission Directorate, that the ones that fly missions to places, including Earth, and observe locations. I work very closely with the associate administrators of the Exploration Systems Mission Directorate, the Space Operations Mission Directorate, the Science Mission Directorate, the Chief Technologist, Leland in the Office of Education, to try and bring all this together. And we have allocated a budget for sort of mission science, human spaceflight science, integrated research activities that is coming forth. It's codified in the fiscal 13 budget, but we're trying to take steps in fiscal 12 to try and integrate those. I do represent to the administrator the Human Research Program, the Life and Physical Sciences. We've recently put forward a reorganization plan that brings those into one organization so that there's a critical mass and advocacy as part of the science in the agency. So historically, the life and physical sciences has been about supporting human spaceflight and understanding biology and physics in the microgravity environment, and it's been a part of the human spaceflight program, because that's where the science has been done. That's where it's been managed. My appointment and the reorganization is really an effort to have a flow of that kind of science up to the administrator level in parallel with the kinds of missions we do. So it's recognized, it's being addressed, and check back with me in about a year and let me know how you think we're doing. And the last thing I'll add is the national, or the space station has just been declared a national laboratory with a nonprofit organization running it, much in the same model as the Space Telescope Science Institute, to generate or optimize utilization of the space station itself. So we're making steps to bring that science forward and integrate it with the other aspects of the agency.
In the interest of full participation from the panel, I think I'd actually like to see if I can shoot something to David Pierce here. And we're talking a bit about what's over the horizon. You know, what's the most amazing discovery you see coming up right, you know, beyond the curve. You have a chance to see some of the technology that's being prototyped right now. And as you said, I mean, this is really the bleeding edge of technology. You test it at a place like Wallops. Could you comment a bit about what you're seeing?
Well, Michelle, what we're doing with our suborbital platforms is we see that the next generation of Earth science instruments are being flown. We're bridging between ISAT 1 and what would hopefully be ISAT 2 with IceBridge. And that's a subject near and dear to Waleed's heart.
Did describe that as an exciting program, yeah.
And working with researchers to be on the cutting edge of advanced instruments that are going to support Earth science, as well as in space science, developing platforms and then taking advantage of commercial platforms that are going to become available to do cutting edge space science work, studying hard X-rays, looking at planetary science from a balloon, where you look at and seeing if you can find or detect a planet around another star, looking at fine pointing and those kinds of systems that we're developing to enable that kind of science. And in terms of cosmic rays, making those kinds of measurements from ultra long duration flights where these platforms will fly for hundreds of days, thus becoming satellites on a string to test out these technologies and do cutting edge science. So that's some of the kind of stuff that we're seeing on our end down at Wallops.
I'm not sure everybody's familiar with Operation IceBridge. This is a fairly exciting thing. ISAT, of course, is the satellite that has been doing laser altimetry, studying the extent of sea ice at the poles. ISAT-1, the original ISAT, stopped operations earlier this year, and ISAT-2 is in development. So between those two satellites, we have a data gap at a time when sea ice is dropping precipitously. And so the IceBridge mission is an aircraft mission.
That's correct. And it's between aircraft at NASA Dryden and aircraft at Wallops, flying over Greenland and going to Antarctica. And hopefully we'll have other platforms up. Global Hawk is a platform that NASA Dryden's bringing online. And can you imagine flying sensors on a Global Hawk that could stay up for 30 hours at a time, and then you could refuel it so it could stay on station for a lot longer, and flying out of West Africa, say flying out of the Canary Islands, and monitoring these waves coming off of Africa to try to discover and understand how those waves turn into hurricanes to help protect our coastline. It's very exciting what's being done to develop these platforms, extend their capabilities to support both Earth and space science.
Yeah, I'll just mention, Global Hawk is a great example of the NASA-NOAA relationship where we're working together with that instrumentation, where we can put these observations where we really need them, using these unmanned aircraft platforms and new observations that we can assimilate into our numerical weather prediction models and really make an impact on society. So it's a good example.
And in these budget-constrained times, I would submit, Waleed, that these these provide a capability to do cutting-edge science while we're waiting to build the next large spacecrafts in some respects.
Well, and as someone who spent months sleeping in 40 below zero temperatures in a tent in Greenland, I see a lot of value to these things.
I believe we have a question from the audience.
Yes. My question has to do with why in recent years the availability of NASA television has become less and less available as cable TV stations, including the University of Maryland TV, have discontinued it. Is there a reason for the lack of interest?
I guess
I think maybe Dean
take
should
a
take that
stab at
one.
that one. We make NASA television available to anyone who would like to air it. We make it available to the public and to cable channels all over the world, or all over the country, and we also now stream it over the internet at www.nasa.gov/ntv. That's www.nasa.gov/ntv. We have actually amplified the audience tremendously thanks to the internet, and we have lots of viewers who are joining us here today via the web. But as for the cable companies, that's their prerogative as to whether they choose to put us on or not.
Actually, one of the things I'll comment on is just sort of, I believe, a change in the media environment as well. I've seen people now look for very specific content. Instead of looking at a beautifully architectured website, which I've spent years of my life trying to create, they will do a Google search on a topic they want, and they will just go right into a third or fourth level page. There's a very much of a directed look at getting exactly what you need. NASA television, and actually TV in general, may be dying away from that idea that it's continuously on, it's something you can plug in at any time, there's some sort of scheduled content. Instead, people want things they can use in exactly the time and place they want. Now, the video that's being produced by NASA in terms of podcasts, video broadcasts, short little things on the web, it's tremendous. I mean, we really have some of the best video producers, the best animators. I'm one of the hosts for the Discovery Channel's How the Universe Works, and probably a good 50% of that show, which is for profit that we don't get, is our NASA animation. With me, that again, I don't get any money for. They come, they film us, they create a for-profit show based on NASA content, and people very deliberately search for a Twitter feed for news about a specific mission. So to some degree, it's a change in the media environment, and I think that television in general, broadcasting in general, is trying to figure out how to respond to that. And in some respects, NASA's been ahead of the curve. We've been doing these very directed, every mission should have a Twitter feed. Every mission needs a Facebook page. Every mission needs a very good video production team to do the podcasting. So it's somewhat of a change in the environment of media, too. We've been talking today a bit about the image of NASA. Somebody commented that there wasn't a human spaceflight person on this panel. One of the things that I've found challenging is telling people about the incredible science that NASA does, when it's true that we have so much to owe the human spaceflight program in terms of inspiration and for the NASA brand, for what people think of when they think of NASA. One question I have for the panelists, another change that's happening soon, I think, is the real branding of NASA as an earth science brand, advocate, for predictions as to what's going to happen, what's happening to the climate, the measurements. We saw a press release out of GRACE, the Gravity Recovery and Climate Experiment, about the Earth literally getting fatter, that water is beginning to pool at the equator because of the melt from Greenland. Say something about how NASA is going to work to actually, we're the nation's space program, but we're also going to become the nation's earth science program.
Well, I'll jump in at that. One cannot do earth science without the space view. I often in talks refer to the Earth, and Tony alluded to this, as a mosaic of stories. It's a bunch of tiles. Each one is an element of what we call the Earth system, and until you put the tiles together and view them from the right perspective, from the right context, you don't really understand the picture that's being told. So while we need boots on the ground, boots in the ice, fins in the water, all of these things to understand the detailed processes on Earth, without integrating them into a systematic kind of view or approach, we will never get the full story, or as full a story as we need to be successful in the face of a changing environment. So NASA really remains a fundamental, not just foundation of understanding the Earth system, but I think the very fabric against which all the elements are, or into which all these elements are woven.
I mean, let me just even answer as an astrophysicist. It's going to be impossible for us to recognize life on another planet unless we actually understand what life looks like on this planet and what the interactions are, because the planets that we will look for will be very different from the ones we're living on. And I think that it's the systems approach. Understanding our Earth system even helps the astrophysicists understand other Earth systems. And I think that's a key linkage that even our own colleagues don't always appreciate on the astrophysics side. It's all part of the same endeavor, understanding a system of life, whether it be here or 25 light years from here.
Yeah, I'll just mention from the weather side, I mean, it's somewhat of a revolution of moving towards this, thinking about the weather problem as an Earth systems problem, coupling the oceans to the atmosphere, coupling the cryosphere, you know, and the biosphere as well. It all really does matter, and so NASA has been certainly a collaborator in that effort with NOAA.
So let me peek into the crystal ball a little bit, looking to the future. Significant changes happened in NASA over the past couple of years where NASA has now taken on the responsibility that the science it does from observing the Earth just can't stop with a data stream after 2 or 3 years. That the science we're studying, the timescales we're studying, require observations that again goes from days to decades. And so totally apart from operations, totally apart from monitoring, the science of the planet is on these longer timescales, and that impacts the science that NASA is doing. But these observations that just alluded to by David, if we kind of go back to the heritage for Earth remote sensing goes back to, as I said at the beginning, observations in support of numerical weather prediction. And I would posit that where we are right now in Earth system science is much akin to where we were coming out of World War II with respect to numerical weather prediction. That our understanding of the physics of the atmosphere at that time, the present state of digital computing at that time, the nascent models of weather at that time ushered in this era of numerical weather prediction. So that we have the forecast that Dave alluded to. I would argue we're at that position now for prediction of the Earth system, and that for 25 years from now, we will have reliable, actionable predictions of the Earth systems, not just weather, but how the Earth acts as a coupled system on these timescales from days to decades. And really, it's all attributable to these fundamental observations that NASA laid forth in the 80s and 90s that go way beyond weather. It's monitoring the Earth as a system, and now we have the prospects for predicting the Earth as a system.
Okay.
I guess with that, we should probably wrap it up.
It's time to wrap up, I'm afraid. I'd like to thank our panel. It's been a great discussion. We're going to take a break now and regroup here at 1:30 p.m. Eastern Time for our afternoon session. Thank you for joining us.